Hello everyone, I'm Pavitra Chandramohan and my group mates are Sitino Antasha, Nurun Afisha and Raiden. The title of the experiment is Minor Losses in Pipe. So I'll proceed to summary. Minor losses are close to major losses where a system with a high K value results in a high loss of pressure. A very abrupt change in the flow directly usually leads to a substantial loss of pressure. Compared to frictional effect, pressure loss is less important as a fluid experience fitting such as pipes, bands, inlets, outlets, contraction, or expansion. As a result, this applies to slightly losses or minor losses. The small losses of a short pipe with many heads and suits may be higher than its large losses, while major losses are more severe for long pipes. The energy losses arise when the pipe and friction force between the fluid particles and the pipe wall is created by an incompressible fluid flow. The kinetic energy is then transferred into heat energy, which cannot be converted back, so it is known as energy loss. Therefore, minor losses can be affected by some factors such as velocity of the fluid, internal diameter of pipe, flow direction of pipe, and the length of the pipe. Next slide. A separate head loss coefficient K can be determined for every element leading to minor losses. K is dimensional parameter to help determine head loss. The coefficient is then multiplied by the velocity head to get the head loss. This head loss can be entered into the Bernoulli's equation to keep an energy balance. This experiment is conducted to understand the relation between loss coefficient and the minor loss in pipe components or fittings for different water flow rates, pipe diameters, and pipe bends such as sudden expansion, sudden contraction, and various branches such as T-type pipe, Y-type pipe, 90-degree bend pipe, 90-degree angle pipe, and 45-degree angle pipe. The small losses lead in general to the level of efficiency of a piping device. In order to better explain the influence of other variables that lead to changes in slightly losses in the piping system, the experiment would link the small loss to various flow rate. The loss coefficient, higher KL, head losses, HL, and vice versa would be larger. The branch from with the lowest loss coefficient would have the least and the most effective losses. All in all, this experiment is conducted to determine the pipe component's loss coefficient and the minor head loss. Next, I will pass to Nafisha.
Alright, so I am Nafisha and I'm going to proceed with the theory of this experiment. So the flow in piping system at different flow rates are required to pass through a variety of fittings or bands that can change the area of the pipe. So when the flow separates, it will cause head losses, which is called as minor head losses. When a fluid travels through a pipe, friction will dissipate energy. So the sum of the wasted energy depends on a variety of factors such as speed, viscosity of the fluid, and also the roughness of the pipe walls if the flow is turbulent. So friction losses will cause the friction to decrease over the length of the pipes and thus increase the amount of power that a pump can provide to sustain the flow through the pipe. So by the flow separation, the 2 points for the horizontal pipe, which is Z1 equals to Z2, can be simplified using Bernoulli equation, and hence the pressure loss and the total head loss can be determined using equations below. So for equation 1, the differential in pressure are divided by the density times with gravity constant equals to the changes in velocity squared plus total head loss, where the total head loss is calculated by adding the major and minor head loss. Major head loss is calculated using equation 3, which is the coefficient of the pipe friction times with the length of pipe times the speed of flowing medium for the tested pipe divided by the internal diameter of pipe times 2g. So next, the minor head loss is calculated using equation 4, where loss coefficient times speed squared divided by 2g and KL can be calculated using the equation as shown in the slide. By rearranging equation 1, we will get equation 2, And then we can substitute equation 3 and 4 into equation 2, which will then govern equation 5. So the KL value of the pipe varies according to the geometry or shape of the pipe components, and also considering the fluid properties, including the Reynolds number. Thus, the mathematical function of KL in terms of the geometry of the pipe and Reynolds number can be written as equation as shown. Next slide. So we have two tested geometrical in this experiment. The first one is sudden expansion or enlargement, and also sudden contraction. The KL value for sudden expansion or enlargement and contraction in a circular duct or pipe can be shown in the figure in the slide. As we can see in the figure, the losses for sudden expansion or enlargement are based on the speed of fluid medium at region 1, while the sudden contraction are based on speed of fluid medium at region 2. The KL value for the fluid flows through a sudden expansion or enlargement and contraction are obtained using the continuity equation, which is equation 7, the momentum equation, equation 8, and also the energy equation, equation 1 in the previous slide, between point 1 and point 2 for the control volume. So equation 7 and equation 8 are rearranged to give the theoretical KL value for sudden expansion or enlargement and contraction as depicted in equation 9 for sudden expansion or enlargement, while equation 10 for sudden contraction. Next slide. So the next tested geometrical is elbows, pipe bends, and also pipe branches. The value of minor head loss and loss coefficient for the flows involving pipe components or fittings such as elbows, pipe bends, and pipe branches are determined experimentally by using equation 3 to equation 5, which I have talked about just now. And then the theoretical values of KL for various pipe components or fittings can be determined using the figure shown in the slide. Next slide. So this is the apparatus used in carrying out this experiment. So the apparatus used is pressure measurement test bench, which consists of inlet valve, two tube manometer tube, tested pipe section, and also outlet valve. So I will pass to Redden to continue our presentation.
Afisha. Hi, I'm Vedan and I'm going to present the procedures. So first, the direction of water inflow and outflow are determined for the tested pipe section. The second step will be the inlet valve of tested pipe section is fully opened by turning it to anti-clockwise direction. The inlet valve for non-tested pipe section is closed by turning it to clockwise direction. Third step will be the pump is turned on and the outlet valve is slowly opened by turning it to anti-clockwise direction until fully opened. The air bubbles for the tested pipe is removed. Next, the inlet flowing pressure H1 and the outlet flowing pressure H2 for the tested pipe section is identified, and manometer tubes is connected from those H1 and H2 of the tested pipe section to the two tube manometer H1 inlet and H2 outlet. Fifth step will be the values of H1 and H2 at the two tube manometer is recorded. Next, the actual water flow rate is determined by recording the time taken to collect the 3 liters volume of water at the tank. This step is followed by the opening of outlet valve is reduced, and steps 4 and 5 is repeated for 5 different values of Q actual. The manometer tubes are removed after finish to avoid the bubbles in the tube. Step 9 will be steps 1 to step 7 is repeated for the other tested pipe section with the pump is running condition. After finished, all the manometer tubes is removed from the system. The inlet and outlet valves is fully closed and the pump and the main switch is turned off. For next part, I leave it to Pavitra.
For the data and result part, different type of pipe is used. Firstly, for sudden enlargement and sudden contraction, the time taken to collect 3 liter volume of water is recorded. Then the Q actual is determined by using the H1 and H2 recorded during the experiment. The last data calculated is the difference in H. Next slide. All the above following is repeated using T-type and Y-type branches, and also 90-degree angle pipe, 90-degree bend pipe, and lastly 40-degree angle pipe, replacing the sudden contraction and sudden enlargement pipes for the enlargement pipes. Next slide. Only for the angled pipe, the time taken is recorded when 2 liters volume of water is collected. Next, I pass to Antasha to proceed with the discussion.
Okay, so for the discussion, okay, next slide. Okay, so first we have to calculate the minor head loss and loss coefficient for each of the pipe components or fittings. So we have to note that to calculate the measure losses calculation, we have to set the temperature of the flowing medium, which is T equals to 36 degrees Celsius. And we have to determine the coefficient of friction using a formula of Blasius. Okay, so, okay, next slide. Okay, so first thing first, to calculate the Reynolds numbers, we have to know the kinematic viscosity, which is 7.1516 times 10 to the power of 97 meters squared per second for the temperature of 36 degrees Celsius. So for the sudden enlargement pipe, the outer diameter given is 0.020 meter and the second outer diameter is 0.032 meter. So to calculate the inner diameter, we have to the outer diameter uh have to minus 2 times the thickness of the pipe. Okay, so for the inner diameter for the first pipe is 0.017 and the second is 0.0284. So for the area, we have to use pi d square over 4. So we have to calculate for both area. And for the formula of KL, 1 minus A1 over A2 square. So for the sudden enlargement pipe, the average minor head loss equals to 0.14674 meter. The average loss coefficient, we get 0.4118, and the average coefficient of friction, we get 0.0222. Okay, so next. Okay, so for the sudden contraction pipe, the same calculation were repeated, but for the KL, we have the slightly different formula, which is 1 minus A2 over A1 square. So, for the average minor head loss, we get 0.07216 meter. For the average loss coefficient, we get 0.4118, and the average coefficient of friction, we get 0.0262. Okay, so next. Okay, so for the Y type pipe, uh, we have the KL. We doesn't have to calculate the KLs. The KL equal. We have to take it from the table, which is KL equals to 2.0, which is the branch flow threaded types. So for the Y type pipe, we get the average minor head loss equals to 0.2668. The loss coefficient is 2.0, and the average coefficient of friction is 0.0253. Okay, so next. For the T-type pipe, the KL equals to 2.0. Okay, same for the Y-type pipe. And the average minor head loss, we get 0.3451. The loss coefficient is 2.0, and the average coefficient of friction is 0.0236. Okay, next. Okay, so for the 2 times 90 angle pipe, the KL is 2 times 1.5 equals to 3.0 because the types of pipe is regular 90-degree threaded. So for the average minor head loss is 0.4578 meter. The loss coefficient equals to 3.0, and the average coefficient of friction is 0.0237. Okay, next. Okay, so for the 2 times 90-degree bend pipe, the type of pipe is long radius 90-degree threaded. So we have to 2 times 0.7 equals to 1.4. So the average minor head loss that we get is 0.1927 meter. The loss coefficient equals to 1.4, and the average coefficient of friction is 0.0258. Okay, next. Okay, so for the last pipe is 2 times 45-degree angle pipe. The type of pipe is regular 45-degree threaded. So we have to times by 2, we get 0.8. So the average minor head loss equals to 0.1221. The coefficient loss is 0.8 and the average coefficient of friction is 0.0237. Okay, next. Okay, so for the second discussion is we have to discuss the effect of different water flow rates, pipe diameters, and pipe bends of the value on the value of loss coefficient. Okay, next. Okay, so the first one is the value of loss coefficient is influenced by water flow rates. This is because if the flow rate is high, the friction loss in the pipe will also be greater. This can be proven with the equation below, which Q is directly proportional to the velocity of fluid, which is Q equals to A1V1. Okay, next, the size of pipe diameters is also one of the factors for the value of the loss coefficient, which is the smaller the pipe diameter, the more friction it will contain and more energy will be lost. Hence, the greater the value of loss coefficient. Okay, next. Okay, so for the last one, the bending of pipes also will affect the value of loss coefficient. The longer the bending pipe, the smaller the loss coefficient. When a bend is provided in the pipe, there is a change in direction of the velocity of flow, resulting in energy loss. Okay, so next. Okay, so this is the last one. The factors that contributing to errors or inaccuracy in experimental data. So there are a few factors that uh, cause the inaccuracy of this experiment, which is the first one is the data is slightly inaccurate. So in this experiment, we should repeat at least twice for each value. So the second is the presence of air bubble in the tube by ensuring that there is no any leakage of the pipes and only take the reading of manometer when there are no air bubbles trapped in the system. Okay, next, the loose connection between rubber and the inlet or the outlet valve. The rubber tube is tightly connected and it can be confirmed if the value with the flow rate from the water meter same throughout the pipe when repeated. Okay, next one is the observer's eye is not squarely aligned with the pointer and scale, placing the position of eye directly perpendicular to the reading of the manometer when taking the reading. Okay, so the last one, the environmental factors such as changes in temperature, vibration, drafts, and electronic noise or other effects from nearby apparatus is also contributing to this inaccuracy to happen. So we have to choose a suitable and quiet place to conduct the experiment. Okay, that's all. So I'll pass to Raven.
Last part of so the last part will be conclusion. In a nutshell, the different types of pipes that were used in this experiment are the sudden enlargement pipe, sudden contraction pipe, Y-type pipe branch, T-type pipe branch, elbow and pipe bends, 90-degree angle pipe, 90-degree bend pipe, and 45-degree bend pipe. There were few variables influencing the loss coefficient and minor head loss in pipe parts or fitting, such as flow speeds, pipe diameters, fluid velocity, and pipe bends. We may infer that if the pipe diameter is larger and bendier, it will cause more loss of energy while the coefficient loss also increases. In addition, because of the greater amount of energy loss, Q increases the volumetric flow rate. For bends, the lower the K value for a bend, the smoother it is, and the opposite is true for a high K value bend. Compared to the theoretical value, the values shown in experiment data are different since certain errors occur during the experiment. The pipe components loss coefficient, Cal value, and minor head loss were determined. Through the data and outcomes obtained, the purpose of this experiment is achieved. That's all from us. Thank you.